The work of Luigi really is the Planetary Atmospheric EDL with Flexible and Inflatable Technologies, and it comes from my bachelor, my recent thesis. And my study focused on the newborn large inflatable accelerators, of which one of the first diagnostic tests has been made with the IRDT2 mission, and it seemed clear since the beginning that this would have been the enabling mission for what concerns mission payloads. And for example, for NASA's design reference architecture for Mars, it has been pointed out that actually the inflatable technology would be the only one to leave enough space for payload for huge masses more than 20 tons in mass, for example. So my work was divided into two main parts, one for the unknown mission and one for the Mascolo. And I developed a specific method code for each one, able to search for an optimum condition for reentry parameters. And for example, the first part of the program had to choose a pair of values for the entry speed and flight path angle to be able to bear the critical condition at the entry, and to search for a loss radius. And the second part had to verify if the payload chosen for the mission would have been loaded inside the capsule. And the third part had to plot the interposable speed versus A, for example, in atmospheric entry. And with obviously the addition of the flexible acceleration. So the first mission that we're going to analyze is the Earth one, and this is an unmanned one, and with no crew on board, which means that all the distinctive limitations in the sizing of the capsule will be more manual, and it would be possible to understand with this one whether the use of the new flexible technology is good and efficient for what concerns performance and weight saving. The first part of my analysis had to go with the equation of motions. I had to understand what were the governing equations during the entry, and so through some simplification, it was possible to point out that the physical trend of the capsule was divided into three main parts. Ballistic entry, in which it was possible to consider the flight path angle and the ballistic coefficient constant with the whole model from the atmospheric interface to the up to a certain level in accordance with the Allen and Kepler's assumptions. And the inflation of the inflatable accelerator, it was in the transient to convert from a ballistic to a lifted design, and so to ensure the change of boundary conditions. And at the end, after once the inflation is completed, the capsule will be in free fall and will land to terminal velocity. And as we are seeing the flow chart, the capsule immensely took place at this moment, and the capsule actually had to sustain structural limitation within the reaction. For example, the maximum load contingency factor, which is the maximum value of acceleration. For this unmanned mission, it was chosen -7.5 for the structural limitation, and for the thermal one, it was chosen 2000 Kelvin as maximum operating temperature for the thermal system. Actually, I've chosen the ablator material, super lightweight ablator 561B. It was one that was used in West editions. And by converging these equations and others, it was possible to find out suitable loss radius for the capsule, and the loadability verification took place right now. And for the Earth mission, it came out that the capsule was able to sustain all the critical conditions, but not to deliver all the payload, so its size had to be increased properly to allow the loadability. At this point, it was able to choose the right accelerator. And for lack of tools, it was impossible to understand the exact value for the diameter, so my choice had to go on trial. Is that the type of accelerator came out from a trade-off between all other missions and from data gathered from other studies. And it seems sufficient for the Earth mission of 150 kilos from ISS to ground to use a single lifter sonic ear. And this seemed a good choice for performance and cost savings, given that this kind of mission, the mission from ISS to ground, has to be repeatable and at low cost. And so here, there are first results. This graph is shows the contour lines for the maximum load continuous factor resulting from the every parallel values from the entry speed and the entry fact flat angle. This mounted curve as minus 7.5 is the structural limitation imposed, and all values above this curve are suitable for their re-entry. And so the automatic program tried to search for an optimum condition and one of the most difficult conditions to enter the analysis, and it found just above the curve an entry speed of 5.77 meters per second with an entry flat at angle of minus 4.96 degrees. By using these values, it was possible to plot the entire course of the descent speed versus 8 in Earth's atmosphere, and it's possible to see that all the critical moments of the descent happens 40 meters above sea level. And the first critical highlight parameter is the head flux, which was equal to 46.78 bar per centimeter squared, which is roughly 99 meters Kelvin. And up next there is the maximum load factor, minus 744, so it's okay with our with the imposed limitations. And the ballistic regime ended with converge actually in the deployment of the first inflatable accelerator, which has been decided to be at 2.665 Mach. So here it's possible to see the transient. The simplified transient had to do on 3 elements 1. So I thought that the transient would have been completed in 2 kilometers of weight, and it has the role of simulate all the adaptive phenomena and pass it from the ballistic regime to a lifted one. And after being a lifted one in free fall, it will be reached at a terminal speed of about 10.4 meters per second. So actually, for this mission, the yet substitute all the systems using the entry descent landing from the hypersonic to the supersonic, subsonic, and even the regime. Instead, the Mars mission was completely different and had to have a completely different approach because there would have been 40 tons in entry, of which 20 landed, and there will be even a crew on board. So this will affect, certainly, the structural limitations to the size of the capsule. And the kinematic analysis didn't differ a lot from the Earth one, except for made for the use of 2 inflatable accelerators to be the deployed subset consequentially. And so it was needed even to use more than one transient to adapt the phenomena from the first ballistic regime to the lifted one, and to adapt all the phenomena in transition between the first accelerator and the second one. And even in this case, using the good results of NASA design reference architecture, it was possible to understand that two accelerators would be enough to accelerate the capsule suitably. The first one with a diameter of 20 meters deployed at 3 Mach, and the second one deployed at 1.6 Mach, that's supersonic 1 or 40 meters in diameter. So the capsule dimensioning took place in the same way, just to ensure human survivability was choosing a maximum load factor of 5.5. Actually, during the analysis, it was searching a value which would have been comfortable. A comfortable value would be less than 4 Gs for all maneuver, but given all the assumptions I've made and obviously the simplified analysis, I prefer to leave a margin of a bigger margin. And even in this case, the capsule was able to sustain all the limitations, but not to deliver all the payload, so it has to increase the size in this case. And as other results, all the values above the further macro line are suitable for the re-entry. And one of the most difficult conditions has been found with an entry speed of 5.09 meters per second and a flat angle of minus 5.05. And we can clearly see right now that the speed trend qualitatively follows the Earth's one, but it happens at a much lower altitude. This given to low Martian atmosphere. So we have in a short amount of time the maximum at flux of 65.83 watt per second square, the maximum load contingency factor, and the deployment of the first EL at 3 Mach. So here you are the two transients. The first one has to balance and under the equation from a ballistic regime to a listed one, and the second one is the adaptation and the increase of the surface exposed area to the airflow. The terminal speed, the resulting terminal speed here is 51.76 meters per second, which actually this means that a landing system is obviously needed, but it seems a good point for the technology being able to substitute even for high masses all the system of for hypersonic, supersonic, and subsonic discouragement. So with this slide, I concluded, and I would like to hear any questions.